So, welcome you all to take part in the third gauge gravity seminar series, the third gauge gravity talk of the season 2. This is a part of online seminar series which focus broadly on the diverse topics in gauge and gravity. And the seminars are held roughly once a month, preferably a Wednesday afternoon. The talks are be recorded and we put it in the CHEP YouTube channel, which is Center for High Energy Physics, located at Indian Institute of Science. And some instruction for the audience. The audience will be muted during the talk, and members can ask a question by raising the hands. And or if there's some urgent question, maybe they can put it in the chat box, which will be communicate to the speaker. And so today's speaker is Frank Saueressig. He is from IMAPP in Radboud University from Netherlands. And Frank did his PhD from Jena University under Thomas Mohaupt. Did I spell it right? Sorry,
Yes.
I pronounced it right? Mohaupt.
Mm-hmm.
Thereafter, he did his postdocs at Utrecht and Sakle, and he was previously a faculty member at Mainz University before joining at IMAPP. He is one of the first few person who showed the existence of a non-trivial fixed point in isoelectric gravity, making it asymptotically safe. So today, Frank will talk to us about asymptotically safe quantum gravity on foliated spacetime. So over to you, Frank.
Yes, thank you for the nice introduction and also the invitation to present our work here. So what I'm going to do in the second half is essentially give an introduction to research that was mostly done by Jian Wang while he was here at IMAPP. So, and you can find the corresponding publications here in this list. So the plan of the talk is the following. So I will start with a general motivation. Since the audience may not be very familiar with what asymptotic safety actually is, I will spend some time on introducing the basics of this idea. And subsequently, I will move to the key topic of the talk. So I want to put asymptotic safety on foliated spacetimes. And then there are some results that we obtained within this framework. So I will focus on the graviton two-point functions and what we learned in this context. And then I will give a small summary and outlook where this research direction could go in the future. But before getting started, so this is a talk on quantum gravity. And quantum gravity research is actually quite diverse. So I put my own cartoon version of the quantum gravity landscape in here. So most people are working here in the direction string theory, holography, gauge-gravity correspondence. Then there's also a branch related to loop quantum gravity, which branched out in spinform models, tensor models. And also our host did significant work on this one. And today, I'm inviting you to explore exactly this tree. So we want to stay within the realm of quantum field theory. And then there are various ways you can go about this. So you can put spacetimes on the computer. This leads to causal dynamical triangulations. And we want to do a continuum approach. So this will leave us with asymptotic safety. So if you wonder where this talk is on the quantum gravity landscape, we will be here in this green bullet today. Now, let's start with the motivation. So our motivation to set this up came from phenomenology. So in what we have seen in the last couple of years is a tremendous progress in understanding gravitational wave signals. So this is depicted here. And also we learn more and more about the structure of our universe, for example, encoded in the cosmic microwave background. And I see this as an invitation to actually test our ideas of quantum gravity. So for the purpose of this talk, we will talk about graviton propagating in a flat background but clearly the framework that we are setting up is versatile enough to be extended also to cosmological background, where we can then learn about tensor fluctuations and potentially also non-Gaussianities from first principles. Secondly, there is a structural motivation coming from the asymptotic safety program itself. So by tradition, this program was inspired by statistical physics. So it mostly worked on Euclidean space-time metrics. Now you can argue this is not very physical. So in the end, you should be able to set up your quantum gravity theory at Lorentzian signature. And then you can have various ways to go for this transition from Euclidean to Lorentzian. And one way is essentially to introduce a foliation of spacetime via the Arnovet-Desarmisner decomposition. So we started this ages ago, but then it only recently went off the ground that we received new results. In parallel, there are also ideas about working with graviton spectral functions. So this was initiated by the Heidelberg group. And then there is another development coming from the area of algebraic quantum field theory. So there the idea is to work completely in Lorentzian signature spacetimes and combine this with the randomization group. So this was initiated by the group in New York. If you start with foliated spacetimes, there are also natural connections. So one natural connection is with Monte Carlo simulations of quantum gravity within causal dynamical triangulations. So essentially, they build on the same topological structure of spacetime as the ADM decomposition. And that makes a natural connecting point so we can compare continuum and lattice computations. I will also briefly say something about the connection to canonical quantum gravity. So in principle, if you have the ADM decomposition, this is precisely what you need in order to transit from a Lagrangian to a Hamiltonian formalism and connect to canonical quantum gravity. Before we are going to introduce foliations, let's first go into the basics of the gravitational asymptotic safety program. So what is the main idea that we have? So first, the program has been extensively reviewed in the context of putting out the Handbook of Quantum Gravity. So there's a section devoted to asymptotic safety, which was organized by Roberto Percacci. And here you can find the corresponding articles covering various aspects of the program if you want to learn more. Now, what asymptotic safety does, it's not the idea of quantum field theory that you learn from a textbook. So this is not going to be is you write down an action, you derive the Feynman rules, you quantize. So the program takes a more Wilsonian approach to finding a quantum field theory. So instead of giving you an action, my starting point is I give you a field content and its symmetries. If you are interested in gravity, then you would say the field content is your space-time metric, G mu nu, and the natural symmetry that you want to impose is invariance with respect to coordinate transformations. And that sets the arena you are going to play with. Then you can start from your field content and symmetries, and in the next step, you start to construct actions from these inputs. So you want to have interaction monomials, O, which you build from the field content and which are compatible with the symmetries. The prototypical example from the metric would be the Einstein-Hilbert action. So here we have the scalar curvature integrated over space-time. So that would be the natural starting point for general relativity. Then you take all the actions that you can construct in this way and you define a huge space which contains all these actions. It's infinite dimensional and it's theory space. Now you can introduce coordinates on the space, and typically these are the couplings of your theory. So they tell you how strong these interactions that we constructed above actually are. Then it turns out that this theory space has an additional structure, namely it has a Wilsonian randomization group flow. So essentially what this tells you is how do couplings change when we integrate out quantum fluctuations of our theory. And these informations, they are encoded here in the beta functions of our theory. Now this was abstract in words. I can also put this into a picture. So we have the theory space comprising all action functionals. Beta functions equip the space with a vector field. We can look at integral curves of these vector fields. These are so-called RG trajectories. And what we are interested in is complete RG trajectories which interpolate between no fluctuations integrated out and all fluctuations integrated out. Now, having this arena, the points that are of particular interest to us are fixed points of the randomization group flow of our beta functions. So this is depicted here. So in the middle of this diagram, we have a fixed point of our flow. Then we have RG trajectories that go away from this fixed point, and they span UV critical hypersurface. So if you want to put asymptotic safety into a nutshell, then the program says that gravity in 4 dimensions has such a fixed point, and this fixed point controls the high energy behavior of our theory. Now, why does this help us? In general, if we have such a fixed point, it gives us predictive power. So typically these fixed points are saddle points. We have attractive and repulsive directions. And asymptotic safety tells you that whatever your theory is, it should be situated within the UV attractive subspace created by this fixed point. So whatever your theory of nature is, it has to be in this gray surface. So not all trajectories will meet this criterion. Here, for example, the green one, this is driven away from the fixed point. So by definition, this is not asymptotically safe. But if you are on this crazy hypersurface, then you see this is embedded in a larger space. And through this embedding, you can make predictions for coupling constants in your theory space, just on the condition that your theory is here in the gray surface. Now we can put this into a more mathematical framework. So suppose we have beta functions. So this is a first set of first order differential equations for our couplings. This is written here. A fixed point will, by definition, correspond to a 0 of the right-hand side of this. So if you sit at the fixed point, you don't go away from it. Then you can linearize the flow in the vicinity of this point. This can be done in a Taylor expansion. The 0th term vanishes by the fixed point condition. So you have the first order term in the Taylor expansion. So this involves the derivatives of the beta functions at the fixed point. And this is a system that you can actually solve. And all the key properties in the vicinity of the fixed point is then encoded in the spectrum of this matrix B. This is called the stability matrix. And there are 2 important properties. So we want to look at the eigenvalues of B. So they essentially encode the scaling exponents or the information about the fixed point. Essentially, this is the universality class that you want to explore. Now, you can divide the spectrum of this matrix into eigenvalues with positive and negative real part. And if the real part is negative, you have a free parameter in this direction. If it's positive, it's a prediction. So essentially, this predictive power of asymptotic safety sits in the spectrum of this matrix. Now, do we have examples of these fixed points? Prototypically, if you do textbook quantum field theory, then you're talking about fixed points which correspond to a free theory. So these are called Gaussian fixed points. And an example where they provide a high energy completion, this is given by QCD. Now, you can generalize to interacting fixed points. And most often they are known from the theory of critical phenomena. So the prototype is the Wilson-Fisher fixed point. And in this case, we have the fixed point governing the long-range dynamics of our theory. In contrast, asymptotic safety says we have such a fixed point, but this controls the high energy behavior of the theory. Now also there we have examples. So gravity in 2 plus epsilon dimensions, you can show that this has such a fixed point. And then asymptotic safety says this fixed point persists up to 4 space-time dimensions. Now, in order to put this hypothesis onto solid ground, we need to have a way to compute actually beta functions. And the tool that allows us to do that are functional randomization group equations. So the idea is to really follow the principles of Wilsonian randomization. So you divide your quantum fluctuations of your theory into high momentum and low momentum, and then you start integrating out fluctuations shell by shell in momentum space. And then there's also an equation that you can construct that does precisely that for you. So this is called the Wetterich equation. It was first invented by Christoph Wetterich and then adapted to gravity about 5 years later by Martin Reuter. And this has become the driving tool in the asymptotic safety problem. So essentially, the object of interest is the effective average action that we have here. And this equation tells you how this object changes when we integrate out quantum fluctuations. Now, formally, what we have here is an exact equation, but it cannot be solved exactly. So we have to resort to approximations. And commonly, we could use perturbation theory. So in principle, we can take the loop corrections on the right-hand side, we expand in a small coupling, and in this way, we can get a one-loop approximation of this equation. In order to investigate interacting fixed points, we would like to go beyond perturbation theory and also resort to non-perturbative approximations. Also, this can be done within this equation. And there are also ways how this can be done rather systematically, depending on the equation of the physics that you are interested in exploring. So canonically, you can resort to a derivative expansion. You can do a curvature expansion or a vertex expansion of this equation. But in general, the way this is evaluated proceeds always in the same way. So in the first step, you do an ansatz for your effective average action, gamma k, and you decide to keep certain interaction monomials that you are interested in. So here you see they are weighted by a coupling constant, and here are the interaction monomials constructed from your fields. You take such an ansatz, you substitute it into your exact equation, and then you project the flow onto the subspace, which is spanned by the OIs that appear here. Then you read off the coefficients on the left-hand side of the right-hand side that multiplies the OIs, and this gives you the beta functions that you're actually interested in. So then you can decide, okay, either I can do this by just projecting on a background. In this case, I evaluate the equation at zero fluctuation fields, or I can project onto correlation functions like propagators. Then I project the equation at a certain order of your fluctuation fields h. So if you want to do this for gravity, and you are looking for an ordering principle, you can do this by a derivative expansion. So in principle, you count the derivatives that appear in your interaction monomers. If you restrict yourself to second order, what you recover in this case is the Einstein-Hilbert action. So this is marked here in green. However, we know that the theory space is not limited to that. So there will be further interaction terms that you can construct for the metric. And here I ordered them in terms of the number of derivatives that appear here. So this line is the 4 derivative terms. Here I've organized everything in terms of 6 derivatives, then it's 8 derivatives, and so on. However, you see from the numbers, since the metric has a tensor structure, the number of independent monomials that you can construct quickly proliferates when you increase the number of derivatives. So exploring a derivative expansion in gravity is technically a hard problem.
Frank, so
yes,
just one question. So in the previous slide, so Riemann cube, I don't see it. This slide, Riemann
yes,
cube is a.
it's here in the
Oh,
5
it's
more.
five more. Okay. I see. Okay.
So I was not able to write all the 8 invariants that I have
Sure.
here in one line.
Yes. Okay. Yeah, thank you.
But then depending on the question that you would like to ask, this ordering principle in terms of derivatives is not the best one. So if you are interested in questions about degrees of freedom, then you see that all the terms in this column here would contribute to a graviton propagator in flat space. And then if you want to have full control of the graviton propagator, you should convert this entire tower into a function of your Laplacian. So this is the step from going from a derivative expansion to a curvature expansion. So in principle, you can also probe infinite projections of your theory space by introducing suitable functions. And this is done here by introducing functions of your Laplacian. If you want to make contact to one loop effective field theory, then you are also bound to this step here from this tower to this function in order to have enough room to actually accommodate the one loop result. Now this is at the level of the background structure. Now we also can have a look at what happens if you want to look at correlation functions of your fluctuation fields. So in principle, then I can expand my effective average action in terms of powers of the fluctuation field. It's depicted in H here. And at second order, this will give me information about the propagator. If I have 3 powers of H, this will be an interaction vertex. And then I can be systematic about this by going to higher order in my interaction vertices. And in practical computations, I will also not be able to include all interactions, so I have to restrict myself as a certain order. In order to be able to do an explicit computation, then I have to do assumption on how to close the RG flow. So technically, if I am interested in a 2-point functions, I need knowledge about 3 and the 4-point function, and somehow I have to do the closure by making an assumption for the highest order vertices that appear here. Now, knowing what can be done, the fair question is, which approximation should I use? And the answer is, this depends on the physics questions that you are interested in. If you are only interested in a hand-waving idea whether a fixed point exists, then a small computation retaining a small number of operators will certainly be sufficient. If you want to see convergence in your results, then you have to be systematic in improving your computation. And one way to do this systematics is by taking the derivative expansion and going order by order in order to see convergence. So then this quickly gets very complicated. Then you can also ask questions about physics processes, like degrees of freedom present at your fixed point, stability properties of propagators, or how does particle scattering at Transplanckian energy works. And at that point, you have to do the transition from a derivative expansion to tracking functions of momenta in order to be able to reliably answer such type of questions. So this is understood. And at the moment, we are on the way of developing the technical machinery to actually go in this and explore this realm. Now, this was very abstract. Let's put this into use in a specific example. So essentially, the scheme 1, projection on small subspaces. So the simplest thing that you can do is you start with the Einstein-Hilbert approximation of the effective average action. So in this case, you contain the Einstein-Hilbert action here. You supplement it by a gauge fixing term and by the corresponding ghost sector to get a well-defined quantum theory. If you choose your gauge fixing to be harmonic gauge, then you have the advantage that all the operators that you have to deal with in the computation appear in the form of Laplacians. So this is very nice if you want to do an explicit computation. Now, once you have specified this ansatz, you can then run the machinery of evaluating the Wetterich equation. So this works algorithmically. So you compute the two-point function resulting from this ansatz. You define your regulator. Then you substitute this information into Wetterich's equation. You evaluate at 0th order of the fluctuation field. And what you obtain is that the left-hand side is the k derivative of gamma. And on the right-hand side, you have to do a trace over an operator. And this operator is sitting in a function of the Laplacian. So for that, we have the mathematical tools to actually evaluate the right-hand side and re-express this again in terms of the curvature monomials that appear here in our ansatz. So in this way, you can get an explicit expression for the beta functions, for the dimensionless Newton's coupling, and the dimensionless cosmological constant. In order to illustrate that this can be done really explicitly, I've put the equations here. So here you see the dimensionless cosmological constant, G, and the anomalous dimension of Newton's coupling. And we also have explicit expressions for B1 and B2. The precise content of this equation doesn't really matter. It's just serving the illustration that we can get this information explicitly. Now, in terms of asymptotic safety, we are interested in fixed points of this system of equations. Since you have an explicit form, you can actually search for the zeros of these functions, and then you find that there are actually two. There's a Gaussian fixed point where G and lambda vanish, and this is a saddle point. But there's also a non-Gaussian fixed point. This corresponds to an interacting theory. So G star is positive, lambda star is positive, and this is UV attractive for G and lambda. And in principle, this is the imprint of the fixed point that we are actually looking for in the asymptotic safety program. You can then check how this fixed point depends on the dimension of your space-time. And here's the corresponding plot. So in 2 dimensions, this fixed point merges with the free theory. For 2 plus epsilon dimensions, it just splits off, so you get a new fixed point. And then you can continuously trace this solution up to 5 dimensions. So in 4 dimensions, you indeed have the interaction, a fixed point that is continuously connected to the epsilon expansion in 2 plus epsilon. Now here's the fixed point data that you obtain here. In 2 dimensions, you only have the 3 fixed points. In 2 plus epsilon, you see there's a new interacting fixed points appearing, and then it's traced to dimension 3, 4, and 5. Now you can also integrate the vector field explicitly. This is done here. So here you see the interplay between the Gaussian fixed point here in the middle and the non-Gaussian fixed point sitting up here. The arrows point from high energy to low energy. So in this projection, all RG trajectories here emanate from the non-Gaussian fixed point, and they cross over to the Gaussian fixed point here, where they exhibit classical behavior. To have the content of this result, it's useful to convert back to dimension-full quantities. So this is the scale dependent of the dimension-full Newton's coupling here. Then you see at Transplanckian energies, Newton's coupling decreases. At the Planck scale, it freezes out. And at subplanckian scales, the coupling becomes essentially constant. So you have a crossover connecting the deep quantum regime associated with the fixed point with classical effective field theory at low energies. So this arises from tracking the flow from high energies to low energies. Now, where are we at this program? So we have an interacting fixed point. This is what we have seen. We learned that this point continues to exist once we introduce meta degrees of freedom. And it delivers a lot of predictive power. So this is specifically interested if we have meta degrees of freedom connected to the standard model of particle physics. So in principle, this predictive power may be able to predict some of the couplings that we have in the standard model of particle physics. We have seen that effective field theory appears from a crossover, and the construction of having such a fixed point also has profound consequences for cosmology and black holes. Also, this has been systematically explored. Now, let me move to the second part. We want to put this construction onto a foliated spacetime. So how do we do this? So the way to go is we want to use the Arnouet-de decomposition of the metric degrees of freedom. So in the previous construction, we had fluctuations h of the full metric. Now we express our spacetime metric in terms of a lapse function, a shift vector, and a spatial metric sigma ij. So what you do at this point, you rearrange your gravitational degrees of freedom. So instead of the metric g mu nu, it's sitting in these new fields n, sigma, and ni. This has two virtues. So first, if you do this decomposition, it leads to a foliation of space-time. So you have a preferred time direction. So that is typically missing if you do a purely Euclidean computation. So you add an additional geometric requirement in your construction. And it's this preferred direction here that ultimately allows you to transit between a Euclidean and a Lorentzian signature computation. Moreover, if you have this foliation structure of space-time present, you get access to new interesting observables. So in principle, you can look for correlation functions at equal time. So this naturally can be incorporated once you have this foliation, and you have the same structure of spacetime as in causal dynamical triangulations. So whatever you compute in the continuum in terms of correlation functions can then be translated into lattice computations and hopefully be compared. Now let me have 2 slides elaborating on these points. So if we have the ADM decomposition, we can do a Wick rotation. And the structure that we introduce allows us to do this without obtaining a complex metric. So let me elaborate on this point in order to appreciate this. So let's start from a Euclidean spacetime metric. So here we have the lapse, we have the shift vector, we have this metric on the spatial slices. And for a generic metric, these fields will depend on both time and your spatial coordinates. In the simplest case, this could be a cosmological metric, then the sigma ij would be the scale factor depending on time. Now, if I open my textbook and look for Wick rotation in flat space, then it will tell me, well, take your time direction, analytically continue to IT, and from that you go from Euclidean to Lorentzian signature. Now, if you do this for this type of metric, where the fields have a time dependence, then suddenly you replace the argument t by the argument it. If you are not very lucky in terms of this t dependence, this produces a complex metric. Now, if we have the ADM fields, we can have a second way to actually do this analytic continuation. So instead of analytically continuing in our coordinate, we can analytically continue in our lapse function. So instead of working with t, we do a rotation of our lapse function from Euclidean to Lorentzian without touching our coordinates. Then you see here, this will swap the sign in front of the t term from Euclidean to Lorentzian without changing these coordinates to be complex. So specifically, the ADM allows us to connect Lorentzian to Euclidean signature computations. Secondly, it also provides the correct framework to connect to canonical quantization. So if we write the Einstein-Hilbert action in terms of ADM variables, the scalar curvature becomes this expression here. So it's the intrinsic curvature on our spatial slices, and here the extrinsic curvature encoding the time evolution of our fields. So we have moved to a relativistic formulation of our theory. Then we can transit from the Lagrangian to the Hamiltonian formalism. And then we see that the n and the I, they turn out to be Lagrangian multipliers. And the dynamics is sitting here in the functions h and hi. So the dynamics is encoded in Hamiltonian constraints. So the framework allows to connect between randomization group flows in the Lorentzian signature and what is done in terms of the Hamiltonian formulation.
Frank, I have a
Yeah.
So in the previous
Sure.
slide, previous one.
Yes.
So when we are making this analytic continuation from NE to INL, so in between, like the n may become a complex number. I mean, the endpoints in this analytic continuation, they are either Euclidean or Lorentzian, but in between, like they can be a complex number. And
Yes.
In that case, the metric may become complex.
Yes, it will.
Okay, I see. So, but we are only like, worried about, we are only like making sure that the endpoints, it will remain basically not problematic. It won't be complex basically then in the endpoints.
Yes.
Okay.
So pragmatically, I would only be interested in working at the endpoints
Okay.
without doing the continuous
Okay.
deformation. However, you can also do this continuously. So Max Niedermeyer and Ruud Banerjee, they worked out the entire mathematics behind this analytic continuation, having this map implemented with a continuous parameter.
Okay, I see. Okay.
So if you're interested on the specific properties of a heat kernel or this class of metrics, they have worked out it all.
Okay.
But this can be found in this reference.
Okay, yeah, thank you.
Sorry, can I ask a quick question?
Sure.
Yeah, so I'm asking that in that case, the heat kernel is convergent or not? Because again, the eyes are always staying. Like, I mean, if you take the norm of it, it would still be convergent. Like if one takes the Fourier expansion of the heat kernel. So that's what I'm asking. Is there a problem with that?
You have to be very careful in defining the heat kernel, and then you can show that you can get asymptotic expressions. So also the details here are found in the work by Niedermeyer, and they have a certain degree of convergence.
I see. Because usually the heat kernel in mathematics defined as a Fourier components, right? I mean, the Green's function, the Fourier component. And if it's like complex, etc., it might not converge. Like e to the power I omega would come as e to the power plus. So that's why I was a little worried. Yeah. Okay.
No,
thank you. I'll look into it.
Yes, but it's clear that you have like metrics with split signature, and then you have to be careful about the convergence of these exponentials in the heat kernel. Now we want to move from these general structural considerations to actually doing an explicit computation, and we want to focus on the graviton two-point function. So the motivation for this comes from gravitational waves physics. So we start with Einstein's equations in vacuum. We expand our metric in terms of fluctuations around flat space. We adopt harmonic gauge. And what we get is a wave equation for our fluctuations h from it. Now, if we are interested in a gravitational wave propagating in the ZT plane, then there are essentially two components in this h. So there's a plus component, there's a cross component. So we are dealing with 2 degrees of freedom. They move at the speed of light. And from GR, we know that they are massless. Now we would like to compute the propagator of this fluctuation field from asymptotic safety. Now the first question that we asked is, where is the graviton? So what field component should we study? So we have the space-time metric. We do the ADM decomposition. So we have elapse, shift, and spatial metric. Next, we introduce the step of going to a background and fluctuations of this background. And for this specific computation, we choose the background to be flat space. So we take fluctuations in a flat Euclidean background for the time being. Then we do a transverse traceless decomposition of the metric on the spatial slide. And this decomposition then identifies what is the graviton. So this is the Hij that sits here. It has 2 degrees of freedom. And you can check that this is actually a field that is invariant when you do a change of coordinates. So the transverse traceless decomposition actually guarantees that you are dealing with a gauge invariant quantity. So this is the object that we would be interested in. Now we can write down the two-point function of interest. So we expand around flat space. We want to have something that is quadratic in the field Hij. And we take a p-squared propagator, and for the time being, we just add a mass to this one. If we vary this with respect to Hij, we get a massive wave equation. And from observations, we know that there are constraints on this mu squared. So it cannot be substantial. So it's not exactly zero based on observations, but we have strong constraints. So the question is, can we meet these constraints based on an RG computation? In order to make the connection here, we then follow the general idea. So we want to project our Wetterich equation onto precisely two couplings. So the GK is a wave function randomization, and the mu k will be the mass of our field. This is what we are going to track. And ultimately, we are interested in the endpoint of our G trajectory. So we are interested in studying renormalized quantities at k equals to 0. Now, if we feed this into the Wetterich equation, on the left-hand side, we have a 2-point function. Then the right-hand side structurally involves a 3-point function and a 4-point function. This you can simply understand at the diagrammatic level. So here we have the k-dependence of a propagator. And here we see there's a 3-point vertex with one loop diagram, and there's a 4-point vertex with a tadpole diagram. And these two structures are precisely encoded in the traces that we have here. So if we want to have the flow of the propagator, then we have to do these types of diagrams. And specifically, we have to have knowledge about the 3-point and the 4-point vertex. Now, in order to get this computation onto a good ground, there were some things that we had to understand properly. The first thing that puzzled us for a long time was how to do a good gauge fixing. So in principle, one is tempted to just set fluctuations in the labs and the shift to 0. However, at the quantum level, this leads to propagators for the other fields which are ill-defined. So you have to come up with something else. And in practice, the something else that works is you want to impose harmonic gauge condition rewritten in terms of the fluctuation fields. So this leads to seemingly complicated expressions, but if you adapt this, then you recover the idea that all propagators for all the components fields are actually relativistic at the level of the 2-point function. Now it turns out that if you do a linear decomposition of your ADM fields into background and fluctuation fields, then you can use the gauge fixing to get Lorentz invariant 2-point functions. However, the 3- and 4-point vertices, so they typically break the Lorentz invariance of your flow. This can be fixed by adding additional terms here to this decomposition, but we have not published this yet. So we know how this works, and we hope to be able to write this up very soon.
Frank,
but in principle, yes.
Just a question. In the previous slide where you are discussing this gauge fixing thing, so this choice of F and Fi, so is there a systematic way to come up with these choices, or like we have to like give trial various things and see which one is like the kind of best fit?
No, you can do this very systematic. So what you can do is you can write down all possible terms that could potentially appear in F and Fi with free coefficient C.
Okay.
And then you look at the combination of gamma graph plus the gauge fixing terms. And then you look at the Hessian in the fluctuation fields. And each component in this Hessian will then depend on the coefficient C that you introduce here.
Yeah.
And then you start fixing all the C's by the condition that everything should organize in terms of Laplacians.
I see. Okay.
And then you ask yourself, okay, I have the number C now. Can I give an interpretation to these numbers? And it turns out that in this way you rediscover harmonic gauge.
Aha. Interesting. Okay, I see, I see. Okay, thank you.
Yes. And the third thing is we have seen that flow equations, they depend on regulators. And in principle for Lorentzian computation, you would like to have three properties. So you want to have the regulator making the right-hand side finite. You want to have the regulator preserving Lorentz invariance. And it should have an analytic structure that is compatible with causality. Now, so far we have not been able to define the golden regulator that meets all these three criterions. Maybe it exists, but it's not known yet. So at the moment, the best you can do is 2 out of 3. And then you can adopt what is important to you. So we opted for finiteness and causality, and at the price of having a regulator introducing additional contributions that prevent you from being Lorentz invariant. But we also checked with other regulation schemes that preserve 2 other properties here. And in the end, the results that you see look structurally very much the same. Now we have the setup. Let's go to results. So what we can do in terms of results is we can study the Einstein-Hilbert action. We can supplement it by scalar degrees of freedom and vector fields. From this ansatz, we can compute the graviton two-point function for the left-hand side, and we also get the closure of the flow in terms of 3- and 4-point vertices. So this is all provided by expanding these actions to the appropriate order in the fluctuation fields. Now then the story evolves quite similar to what we had in the Einstein-Hilbert truncation. You get beta functions, which depend on the number of fields that you have in your system. And the expression that you get are actually very complicated. However, we still find that for the pure gravity case, there is a suitable non-Gaussian fixed point also for the graviton mass and the coupling G. So the flow diagram for pure gravity is here. It looks very similar to the one that we have seen in the Einstein-Hilbert case. We have a non-Gaussian fixed point here. We have a Gaussian fixed point here. But then there's a new feature. There's an infrared fixed point appearing here. So this didn't appear in the background computations that we saw in a simple example. So everything that flows in this quadrant ultimately ends up at this endpoint here. So we have an infrared attractor. Now, what is the physics about this infrared attractor? It's quite exciting. So we have RG trajectories going here. They again interpolate between the fixed point regime on this side, but they quench the value of lambda to be 1/2 on the left-hand side. If you translate this to dimension full masses, that means that this attractor actually drives the mass that we have in the propagator to 0 dynamically. No fine-tuning, it happens here for this entire class. Now you can also analyze how the structure of fixed points depend if you introduce matter fields. Important, there is a set of matter fields where you have a suitable fixed point. This is the orange part here. Then there's a green line. At this green line, fixed points annihilate. And on the right-hand side, the fixed point that we started out with for the UV completion will be gone. Now we can look what the phase diagram in the orange region looks like. This turns out to be the same structurally as the one that we have seen in pure gravity. In particular, the interplay between the non-Gaussian, the Gaussian, and the infrared fixed point is exactly the same. But now we can also go to a configuration where our UV fixed point is actually gone. This is depicted here. So you see Gaussian fixed point gone, but the infrared fixed point and the Gaussian fixed point, they still persist. So while we don't have a UV completion of our trajectories, we still have the IR completion based on this infrared fixed point. So the phenomenon that we have seen here is independent of your UV completion. It is just associated with the infrared properties of your field. Now we can also use this framework to transit to Lorentzian signature. And then we can make specific choices. So if we have a foliation, we can decompose form momenta into their time part and spatial part, and we can use regulators which only depend on spatial momenta. So this guarantees causality. It is good enough to render all the loop computations that you do finite, but since the regulator doesn't depend on form momentum squared, this is not Lorentz covariant. Then I can also invoke the analytic continuation of my lapse function. And then, under these two assumptions, I find that the beta functions obtained for Lorentzian and Euclidean signature are precisely identical. So signature doesn't matter. And we recover essentially the phase space that we already had in the covariant foliation computations with the interplay of the non-Gaussian, the Gaussian, and the infrared fixed point. So everything stays intact once we carry out the computation in Lorentzian signature as well. Now this brings me to the summary and outlook. So for the summary, what we have studied in this talk is the idea of the graviton two-point functions in the ADM formalism. And we have seen that for the two scale-dependent couplings G and lambda, we have a non-Gaussian UV fixed point. This persists for pure gravity and also a wide set of gravity matter systems. And we have seen that there is an infrared fixed point which can drive this mass here to zero dynamically. So this is independent of whether this non-Gaussian fixed point exists or not. And we have seen that once we make proper choices for the regularization procedure, the Euclidean results also hold in Lorentzian signature spacetimes. Now, what would we like to do? So in principle, at this point, we would like to move in the direction of cosmology. So instead of the flat background, which we use presently, we would like to go to a cosmological background and then generalize the two-point function that we have studied here to include higher order terms in the momentum and also make the transition from two-point correlators to three-point correlators so that we can learn about non-Gaussianities. Also, it is clear that once we do the computation at purely Lorentzian signature and in a curved space-time background, there should be new effects coming into the computation which are related to the choice of vacuum state in the Lorentzian signature, which doesn't appear in the Euclidean setup. So also this is a research direction that will be explored in the future. And with this, I'm at the end of the talk, and I would be happy to answer more questions. Thank you.
Thank you, Frank, for the wonderful talk. Now the panel, so we are open for having some questions. So let's say audience can ask some questions also. So in the meantime, so I wanted to ask basically is So in the beginning, like when you say that we can do a vertex expansion and basically a
Mhm.
derivative expansion and the truncations basically. And now, suppose we do the calculation using a truncation expansion and sorry, derivative expansion. And so as I see, like it's more like a kind of a like basis of the vector space. So if I consider it as a, like a basis of the vector space where the basis is basically the various terms in the derivative expansion and the various terms in the kind of this vertex expansion. Now, are the two
Yes.
related to each other or like by some transformation this thing? I mean, in principle, because the equation is exact, so we expect that it
Mhm.
might be related. But since we have to truncate the equation at some in order to extract the results, seems like there might be some that error that might be getting introduced.
Yes. So there's a map.
Okay.
So assume you work in a vertex expansion around flat space. Then you could start with expanding like the Ricci scalar around flat space in terms of fluctuations h. And then you see, okay, at 0th order in h, I will get nothing. But then at first order in h, there will be something.
Okay.
And then you can say, okay, I take this something that I get in first order of h, and I then construct a map that I take the first order in the fluctuation field and I map it to the curvature to power 1. Then I start with an R squared term. There I have to look at the structure that is 2 powers in h, and I map part of the 2-point correlation function back to the R squared term.
I see.
So in this way, you can reconstruct the geometric curvature invariance, but philosophically, you essentially destroy the beauty of working with geometric theory, and you adopt a viewpoint that you essentially do quantum field theory in a flat background.
I see.
And in principle, I think there's also some subtlety about considering or not considering certain vertices in the construction. So the covariant computation might track vertices that are not that truncated away in a fluctuation approach. So you really have to make sure that both sides are sufficiently complex in your computation that this reconstruction really works without errors.
Yes. I see. So there is a couple of questions, and Sayantan has asked a question. He's raised a hand.
So I'll not ask much questions. So one of the question which has been bothering me from a mathematical point of view, so when we do the dynamical system analysis after the gauge choosing, etc., when you are doing the equation, so
Yes.
I'm asking in principle if the eigenvalues are negative, I mean the real part is negative, you can say it's stable, or if it's positive, it's unstable. But if it is 0, it would be very difficult. Like, I mean, it would be like a central manifold and you do not know the stability or not. So I'm just asking, like, from a mathematical point of view, so have you countered such a situations, or in case it happens, even from a mathematical point of view, you have to move to the higher order, right? I mean, the linear theory breaks down, linear dynamical approximation breaks down. So I'm just asking that whether that affects in somehow in your analysis or not. I mean, in case the 0 eigenvalue is there. This is one question, and I have a small second question that. When you got the massive gravity, I mean, that is the after the m square term comes after the renormalization. So I'm asking that how the tensor decomposition still works, because if I understand correctly, when you decompose the Pater metric, there would be scalar modes, like 2 scalar modes and 2 other from the gradient part of the vector and 2 other curl free, and that reduces to 2 tensor mode. But if it's massive, I could not see like how the, I mean, it seems like it is very gauge dependent. Like, I mean, if you do not choose anything other than harmonic gauge, you will not get the TT gauge, because again, the gauge decomposition doesn't work. Like, I mean, you need to have 4 plus 4 plus 2. Like, I mean, so could you just comment on that? How even in the massive gravity, we are still getting the same Hodge decomposition of the metric like that? Yeah.
let me answer the first question about stability of fixed points first. So your assessment of zero eigenvalues and the need of going to higher orders, this is absolutely correct. So when we talk about non-interacting fixed points, it's quite common that you have zero eigenvalues. And then you have to, in physics, this is called a marginal coupling. And then you really have to compute the beta functions and check the sign in order to know whether this is attractive or repulsive. So this, but if we have these interacting fixed points, typically, I don't know about an example where we really had an exact zero eigenvalue.
Because even in condensed matter, when this happens, like the complicated, like I mean, the marginally dangerously stable fixed point. So it was like a mathematical question. Yeah, and second question was the Hodge decomposition, even with the massive. I mean, is it gauge dependence or even it is gauge independent?
So if you have the additional massive degrees of freedom, then they appear at different places of your decomposition. So if you think about massive gravitons, then there will be additional modes propagating in this matrix. But I think I can still work with the subsector that will persist once I send the mass to zero. So in principle, this precisely selected the degrees of freedom that we were looking into, that they are the good ones if mu goes to zero.
I see. So in a sense that if you take a different gauge, it will have propagating modes, like I mean, along the massive direction. Yeah.
If you have massive degrees of freedom, there are more propagating modes, but they have to appear at other sectors of the transverse traceless decomposition. So by construction, the Hij can only carry the 2 degrees of freedom, and everything that is massive has to be here in the tail.
Okay.
So if you are interested in what happens to these extra degrees of freedom, then you also have to track what happens to the fields here in the tail. And we have not done this yet.
Okay. Thank you very much, sir. Very nice talk. Thank you.
So, Frank, there's a question by Subhashis in the chat.
This is a good one.
Yeah, Subhashi is my student. He's pretty good, actually.
So the question is about asking what is the implication if we have a lapse function that undergoes fluctuations. What the fields that we are dealing with here, they are actually mean fields. So in the end, what we have not done is we have not solved equations of motion. And once you do this additional step towards solving equations of motion, then you would look for solutions where actually your background n bar is precisely such that the n hat is 0. And I think in this way, you would at least eliminate the leading order of the fluctuation fields to the background. And how this will work with microscopic fluctuations at higher orders in your fluctuation fields, honestly, I would not know. There is, however, a longer discussion about violation of microcausality in the literature. And I would expect that understanding how these fluctuations might change light cone structures or the proper time debate, this can be tied to the question that is actually asked here about fluctuations in the labs. On the other hand, in principle, you should have the possibility to actually say, I'm gauge fixing my fluctuations in the labs to 0. It is just that we were not able to implement this in any practical computation.
I see. So let's see if there's anything else. Subhashish is saying thank you. So any further questions, anybody? So if not, let's thank the speaker again and for the wonderful talk and giving us the opportunity to listen to this interesting developments in foliated space-time functional hierarchy. And we hope to see Frank again sometime in future. And yeah, thanks, Frank, for the wonderful talk.
Thank you for the nice questions. Okay.
Bye-bye.
Bye-bye.
Stop the recording and we will soon upload it in the YouTube channel and we will share the link in the mailing list. Okay, bye-bye.
Thank you.